Lewis structures can help us to understand bonding in compounds, and we often use them when we're talking about the different properties of molecules. So in this video, we'll learn how to draw a Lewis structure. Before we get started, here are a few things to remember. Larger, less electronegative atoms are usually the central atoms, surrounded by smaller, more electronegative atoms. And when carbon is present, it's almost always the central atom. And carbon atoms are usually bonded to each other, like in this glucose molecule. And since hydrogen can only form one bond because it only has one valence electron, it must be terminal on the outside of the atom. Halogens are generally terminal also. Oxygen atoms are only bonded to each other in peroxides, like hydrogen peroxide here, or superoxides, which react with large heavy alkali metals like potassium, rubidium, and cesium. And in most oxyacids, like nitric acid, as well as most other compounds that contain both oxygen and hydrogen, the hydrogens are always bonded to the oxygens. You can see. The first step in writing a Lewis structure is to determine the number of valence electrons in the chemical species. For a neutral species, we'll add up the sum of all valence electrons on all of the atoms in the compound. For polyatomic ions, we have to take into consideration the charge on the polyatomic ion. For example, a positive polyatomic ion, like ammonium, got its positive charge by losing an electron. So we would take the sum of all the valence electrons and then subtract that ionic charge of +1. For a negative polyatomic ion, like nitrate, which got its charge by gaining an electron, we would take the sum of the valence electrons and add the ionic charge to account for that gained electron. But first we'll go back to our neutral species. We'll use the example of methane, whose formula is CH4. And so carbon has 4 valence electrons, and we have 4 hydrogens, each with 1 valence electron. We get a total of 8 valence electrons. Divide that by 2, and that gives us 4 pairs of electrons that are available for bonding. Our next step will be to determine which atom is going to be our central atom. And since we know hydrogen can only be a terminal atom, and carbon is almost always the central atom when it's present, then carbon will be our central atom. Next, we'll connect our terminal atoms to the central atom. And that will use up all 4 of our bonding pairs of electrons. And so this structure for methane is complete. Larger molecules have a few more steps. We'll follow the same steps for carbon dioxide. Carbon has 4 valence electrons, and oxygen has 6 each. And we have 2 oxygens, so we have a total of 16 valence electrons divided by 2 gives us 8 pairs of electrons that are available for bonding. Our next step is to determine the central atom, and of course we have carbon present, so that'll be our central atom. Then we connect each of the oxygens, our terminal atoms, and that used up 2 pairs of electrons, so now we have 6 pairs of electrons that still need to be placed on the molecule. And so our next step would be to place the remaining electrons around the terminal atoms first. And so when we do that, we'll have a pair here, a pair here, a pair here, 4, 5, and 6. And so now I've used up all of my bonding pairs. If we had any electrons left over, then they would be placed on the central atom. And next we ensure that all of the atoms in our molecule have a complete octet. And since This oxygen has a complete octet, 2, 4, 6, 8 electrons, and this oxygen has a complete octet with 2, 4, 6, 8 electrons. When we look at the central atom, the carbon, it's only got 2 bonds attached to it, or 2 pairs of electrons attached to it. So then, in order to give carbon a complete octet, what we'll do is move a pair of electrons from here and we'll make a double bond here. And then we'll do the same thing to this oxygen. We'll remove that pair of electrons and move it over here to form a double bond. And now you can see that we have 2, 4, 6, 8 pairs of electrons on this oxygen, 2, 4, 6, 8 pairs of electrons on the carbon, and 2, 4, 6, 8 pairs on the other oxygen. And we have a couple more steps to keep in mind. If you're writing a Lewis structure for a polyatomic ion, make sure to put the structure in brackets and then note the charge outside the brackets. And finally, check to see if there are any resonance structures that you can draw and look at formal charges on the atoms to determine which is the most relevant Lewis structure of them. Let's try a polyatomic ion nitrate. We have 5 valence electrons on the nitrogen. We have 3 oxygens, each with 6 valence electrons. And so that gives us 23 valence electrons, but we also have this negative charge attached, which means that we have 1 extra electron here, which gives us a total of 24 electrons, or 12 bonding pairs. Next, we determine the central atom, which is the least electronegative, and that would be nitrogen. And then we connect the 3 oxygens. We've used up 3 of our pairs of electrons here, and so that leaves us with 9 left. Those go first to the terminal atom, so 1, 2, 3, 4, 5, 6, 7, 8, 9. And I've used up all of my bonding pairs. Next, I check to make sure that all species present have an octet. And I can see this oxygen's happy with 8 valence electrons, as is this one, but this nitrogen only has 6 pairs of electrons attached to it. So we're going to need to move one of those pairs of electrons then and form a double bond. So I'm going to take this pair of electrons right here and put my double bond there. All of the atoms have a complete octet. But I could have put that double bond here, or I could have done it here, which means we have possible resonance structures that we're going to draw for this polyatomic ion. And of course, none of these structures is complete until I put the whole thing in brackets and indicate the charge of the polyatomic ion. Now you can try pausing the video and drawing the Lewis structure for this compound. When we add up our valence electrons, we find that we have 26 valence electrons, or 13 pair. So next we're going to determine what our central atom is going to be between sulfur and oxygen, because of course hydrogen has to be terminal. And so the less electronegative of these two is sulfur. So we will make sulfur our central atom. And then we're going to connect the 3 oxygens to the sulfur. So 1, 2, 3. We've now used 3 pairs, so we have 10 pair left. And we will need to connect our hydrogens onto a couple of those oxygens. So I'm going to put 1 there and 1 there, and now I'm down to 8 pairs of electrons, which are first going to go to the terminals, not hydrogen, of course, but we can put 1 pair here, 1 pair here, 1 pair here, and 1 pair here. And 1, 2, 3. And that now leaves us with one pair left over. And remaining electron pairs then are going to go onto the central atom. And so now we've used up all our bonding pairs, and we're going to make sure that all of our atoms in this compound have an octet. And so we can see on this oxygen, we have 2, 4, 6, 8 valence electrons, 2, 4, 6, 8, 2, 4, 6, 8, and on the central sulfur, 2, 4, 6, 8. And the structure is complete. Here's another one for you to try. I count 7 bonding pairs, and it looks like nitrogen's going to be my central atom because it's less electronegative than oxygen. And so I'm going to start with my nitrogen, and I'm going to connect the oxygen to it. I'm going to put it over here. That leaves me with 6 pair. And now I have 3 hydrogens that I need to attach to this compound. And since the compound is written NH2OH, I know that I have to have 2 hydrogens attached to the nitrogen. I'll put one here and one here, and that now leaves me with 4 pair left. And it looks like that last hydrogen is going to be attached to the oxygen, so we'll put that one over here, leaving me with 3 pairs of electrons, which are first going to go on any terminal atoms, and the most terminal one we have here is going to be the oxygen. I can put 1, 2 pair on that oxygen to give it an octet, leaving me 1. Anything left over has to go onto the central atom. And now I've used up all of my pairs of electrons, and the structure is complete as long as all of the species have complete octets that need them, which would be this oxygen, 2, 4, 6, 8, the nitrogen, 2, 4, 6, 8, and it looks like the structure is complete. Boron trifluoride has 24 electrons, valence electrons, which gives us 12 pair to work with. And so the less electronegative here is going to be our boron atom, and we will connect the 3 fluorines to that, leaving us 9 pair. And so, of course, they go first to the terminals, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I've used up all my pair of electrons. Now when I'm checking for octets, I can see that each of these fluorines does have an octet, but this boron only has 3 bonds attached to it. And it's important to remember that boron is an exception and that it forms 3 covalent bonds, as it does in this structure. And so for boron trifluoride, this structure is complete. Phosphorus pentachloride has 40 valence electrons available for bonding, so that's going to give us 20 pair. And our phosphorus is going to be our central atom, being less electronegative of the 2. And remember, halogens are generally going to be terminal. Now, so we have 5 chlorines to attach to that phosphorus. So 1, 2, 3, 4, 5. And I can attach 5 chlorines to that phosphorus, all to that central atom, because phosphorus can have an expanded octet. Since it is in the 3rd period, it has access to d orbitals that will allow that octet to expand. And so this would be an example of an expanded octet. Now I've used 5 of my bonding pairs, leaving me with 15. And so those are going to go around those terminals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we can see that all of those chlorines now will have a complete octet. Our phosphorus is expanded, and this structure is complete. Here's another example of an exception to the octet rule, xenon tetrafluoride, which is going to have 36 valence electrons or 18 pair. And so with xenon as our central atom, we connect the 4 fluorines to it, and that leaves us with 14 pair to go around the terminal. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So now my fluorines all have a complete octet, but I still have 2 pair of electrons that need to go someplace, and according to my rules, anything left over go on the central atom. So I'm going to put them on there like that, and that uses up all of my bonding pairs. And of course, xenon, because it is in period 5, also has access to those d orbitals, and so it can handle an expanded octet. And so I hope you've gotten some good practice in drawing Lewis structures.